Alright, in this video we're going to talk about logarithmic functions. So everything you ever wanted to know about logarithms but were afraid to ask, we're going to try to cover in this video. And there's quite a few properties, so it may take a few minutes here to get through it. If you're looking for information about derivatives of logarithms, that's on a separate video. So is logarithmic differentiation. So if you're looking for those two things, you're looking in the wrong place right now. These are just going to cover the basic properties of logarithms. So one thing, the graph of a logarithm. So a logarithm looks like y equals log, and then we call it a base a of our variable x. And this base a can be any number greater than 0. We don't let it equal 1. But the most important case is going to be when this base is greater than 1. And if this base is greater than 1, this will be a graph of a basic logarithm. So this is the point 1, 0. So all logarithms will go through 1, 0. It gets close to the y-axis, but it never actually touches it. And then it keeps growing, but it definitely kind of tapers out. It stops growing very quickly. So that's the basic graph of a logarithm. Okay, so what the heck is a logarithm? Well, it's kind of a difficult question to answer, I suppose. Computationally, the way that you'll want to deal with logarithms, suppose I have log base a of x equals y. I can turn this into an equivalent exponential, and you write that as a to the y equals x. So this is definitely one of the first little rules that you'll want to commit to memory for a logarithmic function. So let's do a couple examples of these here real quick. Suppose somebody said find log base 10 of 1000. Alright, well, so log base 10 of 1000, this is just some number. I'll call it x. I don't know what it is. But notice this pattern on going from a logarithm. It says if you take this base, a, and raise it to that power, y, you'll set it equal to x. So equivalently, it says I can rewrite this as 10 raised to the power of x equals 1000. Well, don't say it's 10 times 100 because we're not multiplying. You have to think about exponents. So 10 to what power is 1000? Well, 10 squared is 100. 10 cubed is 1000. So it turns out that x has the value of 3. Or we could say likewise that log base 10 of 1000 is a fancy way for writing the number 3. And logarithms, to me, almost anytime I see them, I'm definitely thinking about the equivalent exponential form in my head. Let's do one more here. Suppose I have log base 5 of 1 over 25. So same way, this equals some number x. Well, I can rewrite it as 5 to the x equals 1 over 25. But notice I can write 1 over 25 as 1 over 5 squared, right? 5 squared is 25. And remember, through properties of exponents, I can bring this 5 to the numerator by making the exponent negative. So if you look basically at the left side, it says 5 raised to some power has to equal 5 raised to the negative 2. Well, in that case, it must be the case that the powers are equal, so we must have that x equals negative 2. Okay, so this power up here has to equal this number, so x equals negative 2, and we're finished. So again, log base 5 of 1 over 25 is a fancy way for writing the number -2. Alright, so kind of the first basic properties you'll want to know with logarithms. The next three important properties that are worth remembering are going to be kind of, I don't know, I always consider them kind of the algebraic rules of logarithms. So more rules. It says if you have a logarithm, you know, regardless of the base, it says if we have two things being multiplied, you can break up the logarithm, but it doesn't become the logarithm of one times the logarithm of the other. It becomes the logarithm of one thing plus the logarithm of the other thing. Likewise, if you have division, well, multiplication goes to addition. You may be able to guess that division becomes subtraction. So you'll get log base a of x minus log base a of y. And the other property says if we have something raised to a power, in this case x to the n, there's a rule that says this power can come out front as basically as a factor. You're going to now be multiplying by that power. And notice it's now gone on the right side. So a few more rules that you're going to want to remember with logarithms. If there's a plus or a minus inside the parentheses, you can't do anything with it. You just have to leave it just like it is. So the properties only apply when you have multiplication, division, or one of these powers. Obviously, you know, since there's an equal sign, you can go from the right to the left as well. If you have a logarithm of one thing and a logarithm of another thing, if they're the same base, in this case a, well, you can rewrite the addition as a single logarithm as multiplication. So let's do one of these. Suppose we want to expand let's do log base 2 of x cubed times y over z squared. Well, you could do this in one fell swoop. I'm going to do it in a couple steps. Again, it says if you have whatever's on top, you make it log base 2 of that minus log base 2 of the bottom. So I'm going to get log base 2 of the top, x cubed times y, minus log base 2 of z squared. And I have to be careful here. I can't pull the 3 out because everything's not being raised to the third, just the x. But now I do notice that I have multiplication, so I can break up this first one as addition. And I am going to use this property on my second one over here. It says if you have something raised to a power, you can pull that power out front. So I'll get minus 2 log base 2 of z. And the last thing I'm going to do is pull out this 3. So I'll have 3 times log base 2 of x plus log base 2 of y minus 2 times log base 2 of z. And that's now nice and expanded. The instructions could have started you with the thing at the bottom, and they could have said, well, rewrite this as a single quantity. Basically, you would just reverse the steps. You would take any coefficients and put them up as powers. So all the coefficients would go up as powers. And then if things are separated by a plus, again, they have to be the same base, and they all, in this case, are. If things are separated by a plus, they would become multiplication. And then if things are separated by a minus, you just end up dividing. So it would be pretty simple, I hope, to go back the other direction as well. If this is the first time you've seen logarithms, or it's been a while, it may not be quite so simple. They can definitely be a little confusing. So, but it's one of these things. Once I think you do a few of them and get a handle on them, you'll be okay. Just something notationally that's very important. And I'm not going to do any examples of these, just recall. So this is just notation. When somebody writes log base e, and recall e is just a number, 2.71, and there's more to it. It turns out that e is kind of a very special base for one reason or another. So what they do is we'll rewrite log base e as ln of x, or the natural logarithm. Sometimes people pronounce this ln x, natural logarithm of x, ln of x. So all of those mean the same thing. Likewise, if somebody writes just log of x, it's understood that that means log base 10 of x. Okay, so just some notations. I guess I should put my log base 10 here, but whatever. So these are the ideas. So log of x is log base 10. ln of x means log base e of x. So just something to keep in the back of your mind when you're working with these things. Probably the last important property to really talk about with logarithms are what are known as cancellation laws. Okay, so the cancellation laws. And what this says is, these again tie into exponential functions. It says if you have an exponential, a to the x, and you put that inside of a logarithm, so log base a of a to the x, and notice I've got the same base, that again is crucial. This is going to be equal to x. Likewise, if I have a logarithm, log base a of x, and then I sort of put that inside an exponential, so again log base a of x is, think about that as being a number, and I take a and raise it to that number, that's going to also equal x. And these rules are valid. This first one's valid for all numbers that you can think of. In the second case, this is only going to be valid for x greater than 0. And again, there's some technical reasons for this. Mainly the idea is if you think about log base a of x, if you go back to the domain, if you look at the graph, notice the domain of a logarithm is all x is greater than 0. So we have to start off with those numbers or we're kind of in trouble. If you start off with an exponential function, a to the x, well, exponentials have domains all numbers. Notice you get positive numbers out. And again, those are numbers that you can put inside of a logarithm. The main place you're going to use these cancellation laws are when you have to solve equations that involve either exponential functions or logarithmic functions. So for example, suppose somebody said solve this one. I've got 2 ln of x equal to 1. Well, typical thing I'll do in these problems, if it was just 2 times x, I would divide both sides by 2 and I would be done. I'm going to do that same thing here as well. I'm going to take ln of x and I'm going to get it by itself by dividing by 2. And again, here's where I'm going to use this property. Find a piece of paper here real quick. This is where we're going to use this property. Well, first off, I'm just going to rewrite the natural logarithm as log base e of x. So again, log base e of x, this is equivalent to 1/2. So now I'm going to use this property. It says whatever the base is, you raise both sides to that power, or excuse me, to that base. So I've got log base e. I'm going to take e and raise it to the left side. Well, if I take e and raise it to the left side, I have to take e and raise it to the right side. And by this cancellation rule, it says all you're left with is the stuff next to the logarithm. So now it says I'm left with just x on the left side, and that equals e to the 1/2, which I could also write as square root of e. So square root of e is going to be the solution to this original equation that I started off with. Let's do maybe a couple more of these here. And then we'll be pretty much done with logarithms. Suppose I have e to the negative x equals 5. Well, before I wanted to get rid of a logarithm. Notice I wanted to get rid of a logarithm and I did e to both sides. Now I want to get rid of an exponential. I'll take the logarithm using the same base of both sides. And again, if I refer back to my cancellation laws, it says if these bases match up, they cancel out. So I'm just going to be left with negative x on the left side. Well, log base e of 5, that's some number, and without a calculator I just don't know it. I'm going to rewrite log base e as natural logarithm. Remember, these are equivalent notations. And if I multiply both sides by a negative, I'll get simply that x equals negative ln of 5. And that'll be my answer. Looking for one more good example here. Maybe just one more very basic example. Suppose I have 5 raised to the x minus 3 equal to 10. Well, again, the bases have to match up, so I'm going to use log base 5 on the left side. I'll use log base 5 of the right side. Again, these two symbols match up. Whatever's upstairs, that's what you're left with. Log base 5 of 10, I don't know, that's some number. I'm just going to leave it like it is because I don't know what it is. Now to solve for x, I'll just add 3 to both sides. And again, I'm finished. I've got my answer. You could use these cancellation laws a couple times. So this will be our grand finale here. Suppose I have ln of x equals 1. Well, again, this is log base e. So if I raise e to the first side, to the left side, I'll raise e to the right side. Again, it says if you have e and log base e, whatever's next to it, that's what you're left with. So I'll get ln of x equals e to the first. But I can actually do this again. I can take e and raise it to both sides. And again, now on the left side, I'm just going to be left with plain old x equals e raised to the power of e. And that'll be my solution. So here are some basic examples and some basic properties of logarithms. Again, you know, they're definitely harder examples with logarithms. Trying to give you a flavor of just some of the very beginning ones, some of the more straightforward ones. Again, the things to remember: make sure you know the graph of a natural logarithm, make sure you can convert from a natural logarithm to exponential notation, make sure you know those properties involving multiplication, division, and powers inside of a logarithm, and make sure that you know the cancellation properties of logarithms. So again, quite a few things to remember, but if you do know those things, I've managed to get through a whole career in math just knowing those things. So I think if you know that stuff, you should be in pretty good shape. And I think, again, logarithms are something that you don't encounter that often, so they can be a little intimidating. But I think once you do a few examples and get a handle on them, they won't be that bad. So again, if you need some more help, feel free to visit my website, justmathtutoring.com. Lots of videos on there. Again, if you need to see derivatives of logarithms or logarithmic differentiation, again, those are kind of two different things. Definitely dig around there. I've got some videos showing quite a few examples of that stuff. So good luck. I hope this helps.